Right. So hello, thanks for the invitation. And yes, indeed, I'm going to talk about how in the neutrino field, we're basically getting ready for the future long baseline neutrino experiments or for the future beam neutrino experiments. So just a quick reminder, and for my mother that will probably look at the replay at some point. Uh, so for the last century, the particle physicists have built this crazy good model, which is the standard model of particle physics, that describes how particles interact with each other, elementary particles interact with each other, and there are different specificities. However, well, as any model, we know that it's not perfect. And one of the area of the model, standard model, that we know that lacks information is the neutrino family. So neutrinos are a family of, well, the family of particles that only interacts through weak interaction. And they are considered, well, because they only interact through weak interaction, they are really elusive particle. The order of magnitude that we like to always remind people is that if you take a neutrino, you would need a light year of lead to have a probability of 50% to stop the neutrino. So pretty hard to detect. But there are also, good thing for us, the most abundant particle matter in the universe. So that kind of counterbalance the fact that they're really hard to detect. Why do we like to study neutrinos? Well, we like to study a lot of stuff first, but there are a couple of aspects of neutrino that are not well understood yet. We know that these are massive particles, but we don't know exactly how they get their mass. There are several models, but nothing in the standard model or the way we describe the standard model now predicts for the neutrino to have a mass. We don't know if they are their own antiparticle because, well, they are neutral particles, so nothing technically should prevent them to be their antiparticle. And we know that they undergo some oscillation process that I'll describe a bit later. And that oscillation process is sensitive to charge parity violation to a level that might be big enough to, well, at least give some hints of explanation of why in the early universe there was a tiny bit more matter than antimatter that was created, which at the end of the day, we are in the universe made of matter, so we kind of need to understand that point. And it also helps to probe astrophysical objects that produce a lot of neutrinos, like the sun, like supernovae, and for cosmological early universe events. So for the last century, well, neutrino physics have really evolved thanks to what I would call a succession of anomalies. So it all started the early 20th century when everybody thought, well, physicists thought, okay, we've understood everything. We don't have just a couple of things like the photoelectric effect, but everything is somewhat understood. And there was this beta anomaly where a two-body decay were leading to a really continuous spectrum for the neutrino, for the electron energy. So then that's how the neutrino hypothesis was created. And then 20 years later was the first, led to the first discovery of the first measurement of antineutrino. Then when looking or measuring the number of neutrinos, the neutrino rays coming from the sun, well, things were not really matching between our models for explaining how the sun works and the measurement that we had. We were lacking some neutrinos, and that led, well, to that addition to the measurement of other types of neutrinos, so the muon neutrino and the tau neutrino. And thanks to the Snow and Super Kamiokande experiment that led to the first measurement of neutrino oscillation associated with the Nobel Prize. And now in current days, there are still some anomalies or things that are not fully understood in neutrino spectrums that could be leading to other types of neutrino that we don't fully understand, like possible sterile neutrino, oscillation spectrum shapes, and also future physics to really understand as I said, like the mass of neutrino or the status of neutrinos. So how do we detect neutrinos? As I said in the beginning, right, we have particles that are really hard to detect. So the idea is to have sources that sends you a lot of neutrinos. And we have a lot of different sources. First, some natural sources, so the early universe, the Earth core, some radioactive sources, astrophysical events like or astrophysical objects like the sun. There are a lot of experiments that look at neutrinos from the sun, from supernovae, but also artificial neutrinos like reactor. And what interests us here, particle accelerators. Particle accelerators are great because you kind of can model fairly well your neutrino beam. To create this neutrino beam, what you need is quote unquote kind of simple. You just accelerate really fast some protons, you smash them into a target, then you would create some pions that would decay in a neutrino beam. And if you just focus those pions in the direction that you want, you get a focused neutrino beam. That's, well, on the paper at least, that's fairly simple. And that's what we're going to talk about today. So this is one of the first, or one of the most famous, at least, neutrino picture, neutrino event that was taken in a hydrogen bubble chamber in Argonne laboratory. So just to guide you through what's going on here. So basically what's going on is that you have, yeah, perhaps I can do that like that. Yes, you have a neutrino that is basically invisible in the event here, that interacts here with a free proton in the hydrogen chamber. And you have a muon, an outgoing muon, and two short tracks that are a proton and a pipelet. So this is a typical pion production via delta resonance. So this is a really, typical events from neutrino oscillation, or from neutrino interactions. So that was the case, or that was how we were doing beam physics with neutrino 40 years ago, right? We had bubble chambers, we had simple detector in front of neutrino beams, and we're just measuring with fairly low statistics some neutrinos. Now, what drives the neutrino, what drives the long baseline, or what drives the beam neutrino physics are long baseline neutrino oscillation experiments. So I'll go into details of what those two things mean. So first, the neutrino oscillations. So neutrino only interact through weak interactions, and they're described, the way they describe is that they're created in weak eigenstates, right? There is one specific thing with neutrinos is that they're weak eigenstates. So the way they're produced is a superposition of their mass eigenstates. And we know that particle, when they travel through space, they travel thanks to their mass eigenstates. So that means that the three mass eigenstates of a given neutrino will travel, or will propagate differently. And at a given distance from the origin of that neutrino, well, if you remeasure this neutrino, so if we reproject the three mass eigenstates that travel differently on the weak basis, the weak eigenstate basis, you have a probability that is not zero to find a different neutrino, a different flavor of neutrino. So this is basically explained or presented here in the two flavor approximation. So in the easy case where you would have only two neutrinos, where basically your oscillation is, the amplitude of your oscillation is driven by this angle here, which is a mixing angle between the two flavors. And then the frequency of your neutrinos through space, or through L divided, so space divided by energy, distance divided by energy, is handled by the mass difference, squared mass difference between your two eigenstates. And that's basically what you can see here. So if you manage to put a detector with a ratio, with a distance over energy ratio of 1 meter per MeV or kilometer per GeV, you directly get the maximum of oscillation, and that's how you can probe properly or measure properly those parameters, those oscillation parameters. So in the real case, in our, in the real world, neutrinos are, well, you have three neutrinos. So they are described by what we call the PMNS matrix, which is a product of three rotation metrics. So a product of three rotation metrics that are parameterized with three mixing angles because you have three neutrinos and one complex phase here, delta Cp. And the oscillation, what we want to measure with the oscillation experiments are, well, there are a couple of things that we want to measure. The first thing is the charge parity violation. So basically, if we send neutrinos, or if we look at the way neutrino oscillates and the way anti-neutrino oscillates, do we get the same probability? If we don't get the same probability, that would be that, or if we get this complex phase here non-equal to 0, we wouldn't get the same probability of oscillation, and that could lead, well, that could indicate some charge parity violation, to which we could explain the early universe creating more matter than antimatter. One other thing that we are not measuring properly, well, we haven't measured properly yet, is the mass difference between the neutrinos. So we know we know that you have at least two massive neutrinos, but we have measured fairly properly the mass difference between one neutrinos and the two others, and the two neutrino 2 and neutrino 1. But one thing that we don't know yet, because we're measuring squared mass difference, is the hierarchy. So do we have 3, 2, 1, or one heavy neutrino and two light neutrinos, or two heavier neutrinos and one even lighter neutrinos? And the third thing that we don't exactly know yet, or don't know with precision yet, is this angle here, theta 2, 3, that we have a measurement that is around 45 degrees, but we lack precision in that measurement. So those are the three main goals for the oscillation measurement that we plan to measure for long baseline neutrino experiments. So what do I mean by long baseline neutrino experiments? The idea is fairly simple. Again, in practice it's not, but the idea at least is pretty simple. You have a neutrino beam, you have a particle accelerator, you create a neutrino beam, you send those neutrinos, and you just measure the neutrinos at short distance from the neutrino beam, so where the neutrino beam is created, basically, and at a long distance. So here, for this experiment where I'm working on, which is called DUNE, for deep underground neutrino experiment, the idea is to have a particle detector at around 300 meters, or 500 meters, sorry, and another far detector at around 1,300 kilometers. And then you can do, well, the idea is just to measure both rates, both neutrino rates, and then you can measure, or you can know with precision, your oscillation probability. So this is a map just to show you where the detectors are going to be placed. So we'll have a particle accelerator at Fermilab in Illinois near Chicago that will send neutrinos to South Dakota here at Surf Laboratory. And yeah, that's how, or that's what we're dealing with DUNE detector. So how are we doing things? Well, you have how do you make a long baseline neutrino experiment? You start by digging a big hole. So you can either take a already existing mine or digging the hole yourself, but you really need a big hole because you need to shield yourself from any cosmic events, right? So that's the first step. You dig a big hole. That's what we did. We dug this hole at 1.5 kilometers underground at Surf, so that our detectors will be shielded. Then you put kilotons of whatever material you want for your detection. For us, we used liquid argon because our detectors are liquid argon TPCs, so time projection chambers. Just to give you an idea, so the DUNE will be composed of 4 modules. Each module will be 14 by 15 by 60 meters long. So this is the Scotiabank Arena in Toronto, and you can see that basically you could fit a module. You could fit about 1 module per ice rink. So that's the idea of the size of each module. So then with that you can measure some neutrinos, And the only thing that you need is to know the incoming flux. And that's why you also build a near detector a couple of hundreds of meters from the neutrino target, from the neutrino beam. And for Dune, what we're going to do is to have one near detector here, which will be the same technology as the far detector, so liquid argon time projection chamber. The readout will be slightly different to have a 3D readout, but the idea is the same type of target, so liquid argon. And we'll have other types of detector around it to really constrain the best as we can the neutrino flux, so that we will know really precisely what is our neutrino flux and how what's the flux that goes, or what are the neutrinos that goes to our far detector. So then we have our near detector, we have our far detector. So both rates, right, depend on sigma, which is the cross section, the way the neutrino interact with matter. The efficiency, epsilon, so you just have to know your detector to know the efficiency of reconstruction for a given neutrino event, and the flux. So this is known because that's why we are doing these measurements. And then, well, you just have the ratio of both, and you directly get the far detector oscillation probability. So there are just a couple of issues. The first one is, how well do you know your neutrino interaction models, right? So how well do you know this sigma here? Neutrino interaction models are pretty difficult to build. And I'll just show you in a couple of slides that, okay, there are a lot of caveats on, you just need to know how neutrino interacts. And also, how do you define neutrino energy, right? Because all of those things depend on what we call E nu, which is the neutrino energy. But when you have a detector, that is really dependent on the way you measure it, right? Do you just sum everything that you see in your detector? Do you do some clever physics, assuming that you see a lepton going out of your interaction and you can reconstruct the original neutrinos based on models? It's not fully clear, right? So you have a lot of ill-defined situation here, especially because what we are looking at for those experiments are neutrinos at the GeV scale. And neutrinos at the GeV scale, when they interact, you have a mix of a lot of things. So you have some quasi-elastic, charge current quasi-elastic interactions. So your neutrino interact with neutrino, anti-neutrino interact, neutron or proton, and you get a lepton and a proton, or a lepton and a neutron in the final states. You have pion production, and you have deep inelastic scattering. And if you're in the case of the bubble chamber that I showed before, right, you interact with a free proton, everything is super simple because the initial kinematics is really simple. At the end, you measure everything, and you can directly, if you know the topology at the end, you directly can know what type of interaction happened. The problem is that you don't really want to build several kiloton detector underground made of hydrogen, because, well, it will blow up at some point, and that is tricky. So what we do is that we use heavier targets like carbon, like oxygen, like argon for the case of Dune. And heavier targets are, well, have compound nuclei, right? They have several protons, several neutrons inside your nucleus. And so several things can happen inside the nucleus itself that you won't be able to see with your detector, basically. If, let's say that you produce a neutron inside your detector, and then this neutron can interact, or a proton, and that proton can interact, or that proton can be captured, or something like that. And at the end of the day, what you see, the topology that you see in your detector doesn't exactly reflect what happened. You have what we call final state interaction that are invisible for the operator, that are invisible for your detector. And this is really, well, you have to model it really precisely if you want to go from one final state that you see, one topology that you see, to infer how many, if I see a muon and a proton, how many of them, or if I see 100 muon and proton events, how many of them come from CCQE, how many of them come from a pion resonance where my pion would have been absorbed and I wouldn't see it properly. So really, this is where we need to build really precise models here. So you could think, okay, perhaps our models that we have today are good enough and we need to dig more, right? Perhaps, okay, we need precise stuff, but we already have the precise stuff. So that's true, actually, for the present experiments. because the neutrino rates that we see is low enough, I would say, we are still dominated by the statistical uncertainties. As you can see here, I've represented the total systematic that we have, and the total systematic is, well, definitely dominated by those cross-section models, but it's fine because we don't see enough neutrinos. But in the future, for the two main long baseline neutrino experiment, we plan to have more than 10 times more the statistics for the neutrino program, which will drastically reduce the statistical uncertainty, which is a good news, right? But then we'll be limited by our systematic uncertainty. So we'll be limited by our knowledge of the cross-section models. And that's a bit embarrassing that you have like this crazy technology, you're able to measure thousands, tens of thousands of neutrinos, but you just are limited by the way that you don't know how neutrino interact. So we really need to do better here to, well, be able to match the criteria that we expect for long future experiments. And to do so, well, we have experiments today that took or are taking a lot of neutrino data, and those will help us to build the models of tomorrow, basically. So here I'm going to present the Minerva experiment, which is an experiment I'm working on. Minerva stands for Main Injector Neutrino Experiment for neutrino A. So A is for the number of nuclei inside the number of nucleon inside the nuclei. And it's an experiment that took millions of neutrino interactions for the last decade. It's now been decommissioned, and some of the planes are reused actually for doing prototypes. But yeah, it's a great experiment that took a lot of neutrino data that will be super helpful. So how is it designed? Basically, you have a really high resolution detector made of mostly plastic tracker here. So you have here mostly some plastic, so hydrocarbon. And the tracker is made of planes, and each plane is made of like strips like that. And you have the planes are alternated, so slightly tilted one after the other, so that if you reconstruct some energy deposit with enough planes together, you can have a 3D reconstruction of your events. In addition to the tracker, the main region, you also have a target region. And those targets are made of iron, lead, carbon, and water. And this can add some other measurements of neutrino interaction, but on various nuclei, so that you can do some comparison for various masses of your nuclei to be able to extrapolate more easily your future neutrino interaction models. So, okay, we have our detector, we know what we want to do. Let's build our cross-section. So the cross-section that we usually build are differential cross-section. So it's a cross-section with respect to a given variable. It's not like an absolute cross-section that where we would integrate everything, because every detector measures stuff differently. So it's better if you report a cross-section with respect to a variable that anyone could measure. So that's what make the first idea to report a cross-section would be the total visible energy, right? Because that's, at the end of the day, you're going to measure an oscillation with respect to the energy. So the total energy could be a good idea, but any experiment reconstruct their energy differently, as I told you. So that's a pretty ill-defined, I would say, variable to use. So that's why we mostly use the muon energy. So we have muon neutrino that interact in your detector, and at the end you have muons or anti-muon that go out. So any neutrino experiment, or at least beam neutrino experiment, reconstruct those leptons with a pretty good accuracy. And so you could use the transverse momentum and the longitudinal momentum. So the momentum that is in the same direction of your neutrino beam and the transverse momentum from that, to have a good proxy for both the neutrino energy, so the initial energy, and the transverse momentum for your total in your interaction. And that's usually the main variable. Then people go with like more fancy variables combining the different output particles. But the first variable we usually look at are these two. So let's look at the simplest interaction we can think of, the charge current quasi-elastic interaction. So here I'm quoting CCQE like, because as I told you, we just see a topology, right? We just see in our detector there is a proton and there was a muon. We don't exactly know if it was a charge current quasi-elastic interaction or something else that produced it, right? So you just know the topology, which is basically one muon track. It's super easy to reconstruct. You have a bunch of deposits that follow one track. You can fit it easily. And that track is then detected by a muon spectrometer downstream of Minerva. It's the MINOS near detector and they allowed us to, well, use their data to reconstruct properly our muons. So you have a muon track, super easy to reconstruct. Then you have a short track, which is associated to a proton. So when you have a short track, you usually have two choices. Either it's a proton or it's a pion. The good thing is that proton and pion don't have the same energy deposits per unit of distance profile. And so knowing, well, with the Bethe-Bloch equation, knowing the difference in how the different particles deposit their energy, you can differentiate both of them. And then you look at the end of the proton track after a couple of microseconds, do you have an extra energy that get deposited? If so, that means that you had your short track decayed into something else, and it's most likely a pion that decayed, and at the end of the decay gave a Michel electron, right? So you don't want this, so you just select a short track that looks like a proton and that don't have any Michel electron at the end. And what we do is that we select events without any short tracks and events with short tracks, and we just treat those two differently because it's two different topologies. And at the end of the day, we just merge all our statistics. And you can see here that there is additional energy deposit, right? So here, I didn't tell you, but each small triangle or each small color point represents some energy deposit, right? So you have an extra energy deposit here that are isolated cluster. So those can just be nuclear de-excitation in your detector. So as long as there is just one, it's fine. We keep them. If there are two of them, then it's most likely a neutral pion that would decay into two gammas, and that would say that would give you two isolated energy deposits here. So we have our topologies. We understand how to select our events. We use those cuts I just told you about. Now you need to understand your backgrounds, right? Because at the end of the day, you want to subtract the background components from your signal to extract your cross-section. And to really understand our background, what we're using is sidebands. So you take region where you know that you're going to be dominated by your background. You're just going to have a lot of background, nearly zero signal. And in that region, you fit your background composite. For instance, here, you can select a region where, okay, you had a Michel electron. So the short track that you had was actually a pion, you know it for sure. And so this is the background that you have here. And the purple signal here, well, the purple histogram here, I'm not showing it here. The purple histogram here is actually this single pipeline, this single pion component of your signal. And that's how you do it. You select region where you have only background, you fit your background, and that way you understand better your background component in your signal region. Otherwise, you're a bit too dependent of your initial model, right? So you want to reduce your model dependency with actual data. So you know your background, you know your signal. You just now need to go from the reconstructed space because you measured some muon momentum to the true muon momentum that you measured, right? So this is what we call unfolding. It's just it's just a mathematical method to go with your Monte Carlo to go from, or your simulation to go from the reconstructed space to the true space, and then you've got everything, right? So your cross section can be written like that. So it depends of your unfolding matrix, what you measure here, the flux, the number of targets, which is just the number of nucleon inside your area, the efficiency of your detector, and you have everything. So then you can extract the cross section. So that plot is a bit heavy. So I'm just going to, well, tell you how to read it. So if you go from top left to bottom right, this is the muon longitudinal momentum. So at every panel, the muon longitudinal momentum is risen. Then the muon transverse, for every panel, the muon transverse momentum goes from left to right, and then you have the cross section in Y. And then for every panel, what we report is, well, the data point in points, our model, Minerva-Gini V1, which is the generator that we use, with some tuning that we applied to the generator. And then we also report the breakdown of the different processes that led to the topology that we saw. And that's what you get in the end. And at the first order, our model is quite accurate, right? You can see if you squint a bit your eyes, you can see that, okay, every single data point somewhat agrees with the red line. Things are great. However, if you look in details, there are some regions where we underestimate the signal, right? We underestimate the number of neutrinos that we see. We underestimate the cross section, and that kind of leads us to think that, okay, one or several of those channels have been underpredicted or should be raised to match better the data. So that's one way where you can make your model better or tune your model better, is by doing those comparisons here. So what we actually did then is to look at those data, but not only for hydrocarbon, but also for all the different targets that we had. So for carbon, water, iron, and lead. And well, one thing that you can see is that, so this is what I just showed you for hydrocarbon with respect to the transverse momentum. So yeah, things agreed pretty well. But if you go with heavier material, for lead, for instance, here, well, you start to be, well, you start to do quite wrong with your model, right? And this is one of the reason why it's really important to do that kind of things, that kind of measurement with several material targets, because, well, for instance, if we measure something with argon, which is somewhere in between carbon and iron, well, how do you extrapolate if, well, iron starts to be wrong in your cross section, right? So yeah, that's why it's really important to know that A scaling precisely. So I'm just going to show you quickly another example of a cross section that we extract. So this is charged pion. The idea is a bit the same, right? You have your muon that go inside your detector, and it can interact either in targets or in the tracker. And you have a long track, the muon, that goes out. You have a short track, the pion, that goes out also. And you do the same measurement, right? But then it's the opposite. You look for a Michel electron at the end of the pion. So the pion would decay into a muon, would decay into an electron, and 4 milliseconds afterwards, you would see a small blip of energy just here. And you just want your total energy that is reconstructed in the hadrons to be lower than 1.4 GeV. So you just want to avoid to have a lot of pions that would be produced, and you would just miss them. So you really focus on one pion production here with that additional cut on the hadronic energy. Then the same way we did previously, you have some sidebands. So here the sidebands are cases where a lot of energy was given to the hadronic system. So W larger than 1.4. And also the plastic side, well, we call the plastic sideband for the target region. So here, let's say that you want to measure something, an interaction that happened here, which, okay, that could be an iron target. But what you actually see, you don't see anything in your target, right? You see things in your tracker. So what tells you that your interaction happened inside, yeah, sorry, I was looking at the wrong thing. So what tells you that your interaction happened here inside the nuclear target or just after? So that could be a big background, right? Because you want to know interaction inside iron and not interaction inside hydrocarbon. So to do that, what you just do is you select a sideband where you know that the interaction happened in the plastic, and you know, okay, what's my background here? and then you can constrain the background inside your target. So it's the same way as I presented before. You have those sidebands, you understand the backgrounds, you constrain the backgrounds, and you remove them afterwards. So you do exactly the same way. You have all the information that you need, you extract your cross sections, and this is what you get at the end. So this is a cross section reported with respect to the muon transverse momentum. And I'll just show it here, which is a bit bigger. And you can see that in comparison, right? This before was the charge current interaction, the charge current quasi-elastic interaction, and we were under predicting the data. And you can see that if you just look at the red curve here, so the top curve all the time, we do good in hydrocarbon, but in lead, we start to over-predict the data. So it's the opposite side, right? Beforehand, we were for charge current quasi-elastic, we say that there is less event that we actually see. And for pion production, we say that there is more event that we actually see. So what we think is happening here is that you have a lot of, you under-predict the fact that some pions can be produced inside the nuclei and absorbed. And so at the end, what you just see, instead of a pion and a muon, you just see a muon. And that muon, you say, oh, it's CCQE-like. So that muon, instead of going to that data point here, would contribute to those data points here, right? So you under-predict the fact that the pions can be absorbed, and because you just look at the topology of what's inside the detector at the end, you get it wrong. And so that's why, again, it's really important to measure those, to have those measurements on really different targets to be able to do our extrapolations. So I'm reaching my conclusion here. So for the past couple of, decades, I'd say, a lot of efforts have been made into building the best detector possible with improving our technologies, improving our understanding of how to be built detectors, how to have great readouts, that kind of things. That lead us to, future detectors that have tremendous statistics. And we're reaching a point where, we are limited by our systematic uncertainties, right? So neutrinos, beam neutrino physics, at least, is reaching the point where we are not in discoveries areas anymore, and we're really in like high precision measurements. And for that, we really need experiments like Minerva to provide us really good insight on neutrino interaction models and how to constrain our models the best way. Yeah, that's it. Thanks for your attention.
I'm sorry that I missed, and you may have already said, when you have all of these channels and you have your muons inside of those channels, can you use muon tracks that exceed the volume of the detector, or do you have to only use events that end within the volume?
So that's, I actually didn't explain it really well, but actually we have another detector at the end here, which is the Minos neon detector. It's another experiment that just let us access their data, and they have a magnetized detector. So we can actually see the curvature of the muon and reconstruct properly the momentum. So we actually need the muons to extract exit the detector to have a really good.
Okay, so it's better that it doesn't end within the volume, and it's you.
Yeah, and especially with, otherwise you'd be super limited in the momentum that you can expect.
Yeah, so nice talk. In Minerva measurements, where you're always using new mu measurements, right? So you can see the outgoing muon, right? That's all good to characterize those cross sections. In the oscillation experiments, we're going to look for new E bar appearance, right? So then, do you expect there to be any difference? That's probably not, but is there any new E, new mu cross section differences?
Well, actually, in Minerva, we also do have new E cross sections. Yes, there is a small part of the beam that, it's a small percentage of the beam that are actually new E's that we do measure.
So this is like the nuclear effects, for example. That's where they might come in. Right?
That's a good question. I'm actually not 100% sure of the data of the measurement that we've done in the nuclear targets, because, well, it's only a few percent, right? News that we have. And so, yeah, I'm not 100% sure of what measurements we have.
But at some point, the Dune and Hypercare are going to want to quantify that because they're going to observe the new bar.
Yeah, that's right. I know that there are some measurements or some analysis right now that are done with the more fancy variables. So the transverse kinematic imbalance variables in the new E region to measure the nuclear effects. But we will be heavily statistically. No, there is no argon target inside Minerva. Sorry?
The carbon and the iron data to extract the carbon.
So we have a lot of various we have a lot of various targets. Not argon, that would be between carbon and iron. There are other experiments also that use argon, like experiments like Icarus or like Microboon, that use argon and do measure some cross sections. They don't have the same statistics as we have with Minerva, but that can be complementary results or complementary measurements. But with those data, you can build a model on how to scale up your measurement or your model from hydrogen to lead, for instance, and cross-check those measurements with argon measurements on, okay, does that work? And what precision does that give us? But yeah, indeed, we do not have argon.
They mentioned, Minerva is decommissioned now, and so most of this is just data that's already taken. I'm curious if there's any future experiments that are looking at precision cross-section measurements, or
well, in a sense, Dune and T2K, well, T2HK will look, so because they have where is it? They have a near detector just next to the beam, and those near detector are will measure a lot of neutrino interactions, right? You have those. I know that there are measurements or neutrino experiments right now that can measure some neutrino cross section also, but not to the level of Minerva, which was in the beam line the most intense beam line, measuring a ton of data. I do not know of any measurement that plan to like take over that kind of thing. But I do think that near detector in the future with the beam line that are going to be way more powerful, that still going to send way more statistics, and the detectors that will be optimized that are going to be optimized to measure cross sections. I do think that those will already give you pretty good results too.
Going back to your previous slide, you said you measure the oscillation measured charge pairs for the probability of oscillation to occur between the neutrino and the antineutrino. So you're assuming that these are direct neutrinos.
No, actually, it's because the neutrino and the antineutrino, well, the way they interact is with the W. So you could have a case where you have, regardless of, it could be a Majorana particle, right? It's just that the antineutrino would be the right-handed part, and the neutrino would be the left-handed part. And it's just by the fact that the W interacts only, well, is a chiral interaction, the weak interaction is chiral interaction, you would see a difference here with regardless of the fact that the neutrino is or is not a direct or a Majorana.
That would affect the mass process, the mass creation process, but not necessarily the
Operative value. I mean, you could have both.
Do we have any other questions? All right, well, let's thank that again.